All right, everyone. Hello. Today we're going to learn about how to teach machines the meaning of words. Have you ever wondered how do we teach machines the meaning of the words? And let's think about what it means. What it even means, like the meaning of the word. It's a very non-trivial task because if you take these two sentences as an example, I ate sweet apple for breakfast. And the second sentence, Apple announcing the new AI model. You can imagine that the same word apple has different meanings in these two sentences. In the first, it refers to a fruit apple. In the second, it refers to a corporation. And why do we want to teach machines the meaning of the words? Well, because it's useful. For example, if machines could understand the meaning of the words, then they would be able to also identify similar words, which would allow us to search for documents based on a keyword. When I search based on a keyword car, ideally, I want the computer, the machine, to also return me the documents which mentions the word vehicle because they have similar meanings. And how have smart people approached this problem historically, traditionally? Traditionally, they built something called thesaurus, which is a huge vocabulary of synonymous words, similar words. But it has problems, of course. And what are the problems? But first, it's a manual work. Scientists meticulously documented synonymous words, documented similar words. Hard work means high cost. Second problem is language evolves over time. It's a living thing. It's almost like a living organism. The new words start emerging, or the same words start acquiring a new meanings. For example, decades ago, when computers didn't even exist, the word processor could mean completely different things. It People wouldn't really think about it as we think about them today as chips or computer also might have had a completely different meaning. It could be referring to a person who computes. Uh, but today we know when we say computer, we are talking about machines. Also, the same words start acquiring new meanings like heavy, in the sense that something that requires deep thought, like a lot of thinking, a lot of brainstorming, or which stirs our emotions. These things, uh, like heavy, could mean that kind of thing. But of course, the original meaning of the heavy was an object which weighs, which is heavy, which weighs a lot of kilograms. Also, thesaurus cannot really capture the nuances of each word. The words like vintage and retro, they could be similar, but they're used in different contexts. Mind, the words mind and heart, they could have similar meanings in certain contexts. Speak your mind, speak your heart, but you cannot really use heart in the case when you say mind your own business. Or you cannot really say like in my mind or in my heart. That could be, but still. Or you cannot use mind as an organism, heart. All right. The natural question arises, well, isn't there a better way? Can't we do better? As it turns out, yes, there's a better way. How about we count how many times the word of interest co-occurs with other words? You could argue that similar words tend to co-occur with similar words, such as when you say, I go to school, I go to cinema, I go to zoo. We could argue that this word go tends to co-occur with a noun and a place. Somebody goes to somewhere. This is a powerful statement that really impressed me when I uh, encountered it the first time. A word acquires meaning in a context. A word by itself has no meaning. This really takes you to the philosophical thoughts about what is the meaning of life or what is the meaning of the person by itself. The person by himself alone cannot really survive, cannot really exist, or doesn't really have a meaning. It's only in the surroundings of crowds or its close people does it acquire meaning. I acquire meaning in my family. I acquire meaning in my community, and so on and so forth. So the context, when we are using when we say context, what we really mean is simply the words surrounding the word of the interest, the target word, right? For example, in this famous line from Eminem, uh, "Lose Yourself" song, the first line, which goes, "If you had one shot, one opportunity, seize everything you ever wanted." So in this case, if we focus on word "you," the words "if" and "had" become a context, and later again, uh, we have the same word "you," and "everything" and "ever" become the context. In this case, we are treating one word right before and right after the target word as context, but we don't have to limit ourselves to just one word. We could extend it to two words. For example, in this case, we could treat "everything," "sees," and then "ever," "wanted" as the context of the "you. And we could extend it to N words, not just one, two, three. And all right, so how do we do this? How do we count co-occurrence of words? Usually what we do is we count this in a huge corpus. And what is corpus? A simple definition of corpus is just a huge text. Think about novels, news, blogs, Wikipedia articles. Corpuses can also be advanced. The words could be tagged with part of speech for identifying whether it's a noun, whether it's an adjective, or whether it's a verb. For our purposes, we'll just think about corpus as a text, as a huge text. And we could use co-occurrence as vector representation of the word. And you should know that computer is very good with numbers. If we can represent the word as a series of numbers, then we can start doing some interesting things that you will see later. So here I am explaining the process how to build a co-occurrence matrix. Suppose you had a corpus, uh, a very huge corpus, perhaps with 10 billion words, but it only used 1 million distinct words. So it is using 1 million distinct words, but of course, the same word could be appearing many, many times in the corpus. And what you would do, so what you would do is to build a co-occurrence matrix, you would focus on every word, on each word in your vocabulary, and you would be counting how many times does it co-occur with other words in that corpus. And you end up with 1 million by 1 million co-occurrence matrix. And every row becomes the vector representation of the word. And because you're dealing with a matrix, you need to assign some integer ID to every word so that later you can extract that particular row number from the matrix. We will see this in a particular example later. This one we already mentioned, so unigram, bigram, n-gram, this thing that we're trying to do, we're trying to represent the word as a vector of numbers by counting, by building the co-occurrence matrix. And this kind of modeling is called n-gram modeling, because what you're really doing is you're counting how many times the target word co-occurs with n words right before and right after the target word. All right, let's take a very simple example. Suppose that our corpus was tiny sentence which goes, I had a good sleep yesterday. Suppose that this was our corpus. So how would we go about building its co-occurrence matrix? Well, of course, we would list every word in the vocabulary, and because every word is appearing once, only once in my corpus, uh, it literally becomes my vocabulary. So I had a good sleep yesterday, and even the period becomes is a word. I will treat it as a word in my vocabulary. So I have seven. 1, 2, 3, 4, 5, 6, 7. And my co-occurrence matrix will be 7 by 7. 7 by 7 matrix. And I go counting. So I co-occurs with head, so I put 1. Head co-occurs with I one time, and it also co-occurs with A one time. So on and so forth. And I will end up with this kind of matrix where it has ones on diagonals like this, and everywhere else it is empty, meaning it will have 0 values. And if I were to uh, represent the particular word good as a vector, it would be 0, 0, 1, 0, 1, 0, 0. So that would be the representation of my words. All right, let's now write some code.